Today we are going to discuss a critical operational parameter in blast furnace management, the oxygen ratio, often denoted as P, specifically within the context of pulverized coal injection or PCI. Understanding the controlling this ratio is key to maintaining furnace stability and efficiency. So let's start by defining what this ratio actually represents. So, what exactly is the oxygen ratio? In simple terms, when we inject pulverized coal into the blast furnace, that coal requires oxygen from hot blast to combust. Think of it like any fire, it needs fuel and oxygen. If you push in too much coal without enough oxygen, it simply would not burn properly. The oxygen ratio P is a straightforward way to quantify this balance, and it is the ratio of the actual oxygen supplied by the blast to theoretical amount of oxygen required to completely burn all the injected coal. This simple metric gives us powerful but real-time indicator of combustion condition inside the furnace. Now the formula and its meaning. So let's look at the formula and what the number tells us. As you can see, the calculation is a direct comparison. The oxygen you have versus the oxygen you need. And this is a right comparison. If P equals 1, you are in an ideal scenario, a perfect stoichiometric balance where every bit of coal has just enough oxygen to burn completely. If P is greater than 1, you have extra oxygen. This is generally a safe operating condition, but it might be inefficient as you could be using more oxygen than necessary. The real danger lies when P drops below 1. So, danger is here when P drops below 1. This indicates an oxygen deficit. The coal will not burn completely, resulting in creation of unburnt particles, which causes significant problem that we will explore next. Now, the critical threshold. Why P is equal to zero point 0.7 is important now. You might think any value below 1 is bad, but experience and operational data have shown there is a specific critical threshold we must watch, an oxygen ratio of about zero point 0.7. As long as the ratio stay above zero point 0.7, the furnace can generally cope. Combustion efficiency remains acceptable and any unburned material is manageable. However, the moment P drops below this zero point 0.7 mark, the situation deteriorates very rapidly. A significant amount of coal dust escape the raceway without burning. This has a cascade of negative effect. The raceway temperature drops and these unburned carbon fines start to accumulate in critical area like the dead man and tripping zones. This buildup clogs the furnace, reducing its permeability and severely compromising the overall stability of operation. Now coming to the oxygen ratio as an alarm system, because the consequences are so severe, an oxygen ratio dipping below zero point 0.7 is treated as a critical alarm signal. It's the furnace ways to telling us there is too much coal for available oxygen. When this alarm is triggered, immediately action is required and operator have two primary levers to pull. Either reduce the amount of fuel by rolling back the coal injection rate, number one, or increase the available oxygen by adding more oxygen enrichment to the hot blast. This quick response is essential to restore balance and protect the furnace. Now, just To briefly illustrate how the required oxygen is calculated, let's look at the quick example. For 1 kg of coal, with a typical analysis, we calculate oxygen needed to burn its combustion elements, carbon, hydrogen and sulfur, based on their chemical reaction. We also subtract the oxygen already present in the coal itself. In this case, we find that this particular coal requires 2.3 kg of oxygen for every kilogram of coal injected. This number becomes denominator in our oxygen ratio formula, which is then compared against the actual amount of oxygen being supplied through the 2 years. So to conclude, the oxygen ratio is a simple yet powerful parameter for managing pulverized coal injection. Keeping P above the critical 0.7 threshold is a fundamental to ensuring a stable, efficient and safe blast furnace operation.